Hey everybody. So I just wanted to show everybody how to work the chapter 6 activities. So let's begin with figure 1. And I know we went over this a little bit in class in one of the courses, but not in all of them. So in figure 1 are the glucose molecules that are reacting in the condensation, alpha or beta anomers. All right, so the answer to this is going to be alpha, right? It's going to be alpha. So you look, what do? You look for your anomeric carbons, all right? And so if you're looking at your disaccharide or you're looking at your monosaccharide, you can see here, right? You have this hydroxyl facing down and this carbon 6 group up. That's across from each other, so that's trans. That's alpha, right? And you see this is the anomeric carbon that is participating in the condensation, right? Here's another anomeric carbon, it's bound to 2 oxygens, but it's not participating in the bond, right? The linkage. So this is, in fact, the glycosidic bond, and this is alpha. Down, up, that's trans. Those groups are across from each other on the sugars, that is trans, and it is known as an alpha glycosidic bond. Okay, so alpha anomer. All right, which carbons are bonded in that glycosidic bond for maltose? So in the 2 glucose units, you have, this is carbon 1, 2, 3, 4, 5, 6. On this first one that's participating in the glycosidic bond, and you have also 1, 2, 3, 4. Oh, that's the one in our bond. So we've got 1 on the left, right? And we've got carbon 4 on the right. All right. Of course, you see why the glycosidic bond in maltose is called an alpha 1,4 bond, right? You're talking about the configuration of the hydroxyl to the carbon 6, where the on the sugar where the glycosidic bond is made on that anomeric carbon. So you're denoting the configuration of the anomeric carbon that's involved in the glycosidic bond, and you're denoting the 2 carbons that are on the 2 different sugars that are involved in the bond. Okay, 1 to 4, and you list the carbon that's on the anomeric carbon that's involved first, right? So now you have to denote, and I don't know why these answers are given here. I hope not all of the answers are written here. No. Anyway, but let's work out how you get these. All right, so you have D-maltose, and we just worked this. This is an alpha 1,4 bond. All right, so this is the glycosidic bond. They want us to determine the glycosidic bond in D-lactose in table 1. All right, so the glycosidic bond that's going to be happening in D-lactose, we find our anomeric carbons. So there's one here, right? There's an anomeric carbon here. This is the anomeric carbon that's involved in the glycosidic bond. And what's the orientation? Up. Carbon 6 group up. That is cis, right? So that is beta, and this is carbon 1. All right, and this is 1, 2, 3, 4, 5, 6. So 4, so that's beta 1 arrow over 4. And that is how you work that one. All right. Next, we have D-sucrose. The glycosidic bond in D-sucrose is different than most designations because both anomeric carbons condense to form the disaccharide. All right. So know that we have this 6-membered ring. All right. So this is our pyranose. And in this case, the anomeric carbon is going to be carbon 1. And here we have our 5-membered ring. It's a furanose. Okay. And so in this case, our carbon 5 is going to, our carbon 2 on the 5-membered ring is going to be our anomeric carbon. And so you see both anomeric carbons, right? They're both bound to 2 oxygens. Both anomeric carbons are involved in the glycosidic bond. So that has to be noted whenever you're naming the glycosidic bond. So you have to look at the orientation of both of them. Well, okay, so you have down and up. All right, so that's alpha. And here you have up and up. So that's beta. And you have carbon 1 first involved and then carbon 2. So this is how you write this out. All right, alpha, beta, 1, 2. All right. And it says label the monosaccharides in sucrose as alpha D-glucose and beta D-fructose. Right? So this is our alpha D-glucose. And this is our beta D-fructose. All right. So we want to locate and name the glycosidic bond for the following disaccharides. All right. So we're going to find our anomeric carbons. 1, right? 2. They're both bound to 2 oxygens, right? So it's easy to find. What is the glycosidic bond? Well, this one is not taking part in the glycosidic bond. This anomeric carbon is taking part in the glycosidic bond. This is taking part in the bond, but it's not an anomeric carbon. So the glycosidic bond is right there. Glycosidic bond is right here. Okay. So that is what? Up and up. Cis. So that is beta. That's going to be beta. And that's on a carbon 1, right? And 1, 2, 3, 4, 4. So this is the name of the glycosidic bond. Okay. I think we might have forgotten to answer number 6. Why do the glycosidic bonds in maltose and lactose only contain either alpha or beta, and sucrose is alpha beta? Well, so only one anomeric carbon, participates in the glycosidic bond, right? So that's what's happening for maltose and lactose. And for sucrose, that's different, right? That's why these two are reducing sugars, maltose and lactose, but not sucrose. Okay, so we've done A. Now let's do B. We have, right, our anomeric carbon here, and we have an anomeric carbon right here. And we have a carbon that's involved in this bond, but it's not anomeric. This carbon is anomeric and it's involved in the bond, so this is the glycosidic bond. And orientation, our oxygen, our bond is down. Our 6-carbon group on the ring that has the anomeric carbon that's involved in the bond is up. So down and up, that is across, they're across from each other on the ring. That is trans, which is alpha. So alpha, that is 1, and this is 1, 2, 3, 4, 5, 6. So it's off of the 6 carbon. So that's alpha 1, 6. There you go. That's the name of the glycosidic bond. So, all right. Somebody should describe how you determined the glycosidic bonds in your group. All right, in those disaccharides. So what did you do? What did we do? We identified what? The anomeric carbon. Participating in the glycosidic bond. Okay. Then you put in parentheses with an arrow between the numbers. Right? Like this. All right. And then you had to identify, right? Identify the orientation of the glycosidic bond as alpha or beta or both. And you place that before the parentheses. All right. So next, we are going to identify this reaction as condensation or hydrolysis and provide the products. Well, this is a disaccharide and we've got a water. So we're going to have hydrolysis here, right? We're going to break up this disaccharide. So this is going to be hydrolysis. Okay. So you can think of this as just R1 bound to oxygen bound to R2. And your products are going to be R1 hydroxyl and R2 hydroxyl, right? So this is going to split, all right? And you're going to have your water molecules there, right? That are going to be breaking this up. The water is going to break. And each one of these sugars, all right, one of them is going to take an oxygen and a hydrogen, and the other one that has hydrogen is going to take an oxygen. So you're going to end up like this. Okay. And HOH, HOH, OHH, HOH, and CH2OH. All right. So you see what I did here? Plus. All right. So this is here. Okay. Now do the same thing, only you're going to have this hydroxyl that's going to be facing down. All right, and you have your 6 carbon group here, of course, and you have your hydroxyls and other hydrogens just the same as before. I'm just repeating what I just drew. All right, and so you're going to have 2 hydroxyls, then this is going to divide, and you're just going to have 2 hydroxyls facing down. Right? I'm just going to do this. So this seems to be what gives people problems. So this is just going to split up, and you're just going to have, instead of this and this, you're gonna have this. That's it. That's all that's really happening, okay? That's your answer. All right, let's do B. Okay, you guys are getting this, I bet. So this is going to be, right, we're adding these together, condensing them. That's condensation. Okay, we have, let's draw our rings, right? So we know this is where we had our hydroxyl. Okay, this is where we're going to have that bond between the two sugars. So, all right, we're going to draw our other ring now attached. And we're going to have our hydrogens just how they were. And you just fill everything else in the exact way it was over here. Okay, OH. Oop. OH, H, right, HOH, and likewise. All right, and it's just as easy as that. Now we are going to circle the glycosidic bond in the following carbohydrates. All right, so our anomeric carbons here, this is the one that's involved in the bond though. So this must be our glycosidic bond. Okay, so here is our anomeric carbon. All right, and here we have a carbon, but it's not the same, right? This is not our anomeric carbon. So the one that's involved in the bond that's anomeric is this one. All right. Malazotose is a trisaccharide found in honeydew. It's the structure below. So it wants us to name the glycosidic bond between monosaccharide A and B. So A and B, all right, here's the glycosidic bond. Here's our anomeric carbon here. And we have another anomeric carbon here, but it's not involved in the glycosidic bond. This one is. So this is the glycosidic bond between A and B. And so this is down. Our 6 carbon group is up. They're across from each other. So that's alpha. This is 1. And this is 1, 2, 3. Remember, that's a 5-membered ring. So it's going to be alpha, 1, 3. Okay. This trisaccharide contains fructose, right, and glucose. So label glucose and fructose malazotose. All right. So let's just say, let's go by A, B, and C. So the monomers that are A and C are glucose, right? Those are our 6-membered rings. And our monomer B is fructose. Okay. So I think that's all we have to do for this one. All right. So let's do our reducing sugars activity. And you can pause the video if you need to. We'll do our reducing sugars video, though, in the same shot. So, oxidation and reduction. So, a positive Benedict's test for reducing sugars is shown for D-glucose, right? So you remember, this is going to be where we're adding our, we have our samples that are going to have our sugars there. We have our functional groups, okay? And we're going to add our Benedict's reagent. So we had our copper ions, and we're going to have our oxidation reduction, and we're going to have a product. We have a precipitant. All right. So that's going to be a positive Benedict's test. All right. But is the D-glucose undergoing oxidation or reduction? So the D-glucose is going to become gluconic acid. It's going to become gluconic acid. So what happened here? Gain an oxygen. Do you see that? You gained an oxygen. So is that oxidation or reduction? Well, that's oxidation. All right. Now the copper 2 ion, did that undergo oxidation or reduction? Well, it became Cu2O. Okay, the insoluble product. So was it oxidized or reduced? Oxidation, reduction. So that's a +2, right? We remember this. So let's see. If we have copper 2 and oxygen, then we know this was where our 2 came from, and our copper then must have just been 1. So if we have copper 2 goes over and it's copper 1, that means it's going from this very positive to less positive. So that means we gained 1 electron. So that means we were reduced. So that's reduction. Reduction happened. Reduction. All right. So we need to locate the anomeric carbons on all of the following carbohydrates. All right. And that's because we want to find out what's a reducing sugar. An anomeric carbon not in a glycosidic bond is going to make a reducing sugar. It's going to make for a reducing sugar. So in this case, alpha D-glucose, this is our anomeric carbon. It's free because all monosaccharides are reducing sugars. So this is a free anomeric carbon. So it is a reducing sugar. It's a monosaccharide, so you know that. It's easy to tell. All right, this for our fructose is our anomeric carbon, all right, 2, carbon 2, that's where it folds back on 2. So C2 is the anomeric carbon, and it is free, and it is a reducing sugar. It's a monosaccharide. D-lactose. This is an anomeric carbon, and this is an anomeric carbon. So, all right, this is C1 and this is C1, but this C1 is not free. This C1 is free. All right, so this is a free anomeric carbon. So D-lactose is a reducing sugar. D-sucrose, carbon 1, carbon 2. All right, because we have our glucose and our fructose, right? So they are both anomeric carbons. And this is not free carbons, and it is not a reducing sugar. Okay, so moving on, number 4, based on the definition, which of them are reducing sugars? Oh, we already did that. So reducing then that is alpha. It's based on whether or not you have a free anomeric carbon. So that's all monosaccharides, right? So alpha D-glucose and beta D-fructose and even D-lactose. But non-reducing, that would be D-sucrose. All right. So now we're going to do some oxidation and reduction. All right. Again. So ribitol is found in the vitamin riboflavin. It's formed from D-ribose. We talked about ribose. The reaction is shown below as the reaction in oxidation or reduction. All right. So what has happened between these functional groups? Add hydrogen or oxygen? You added hydrogens here. If you added hydrogens, that is reduction. Right? So if you draw them out, your Lewis structure type of way, all drawn out, you can see that's what this is. And you have now a hydrogen bound to this oxygen, right? And carbon is bound to two other hydrogens, make carbon happy. Of course, it's still bound to this carbon. So that's what happens with reduction. You're adding hydrogen. This is what's going to be the result on that functional group. All right. Are the following carbohydrates reducing sugars? So D-mannose, yeah, that is a reducing sugar. Why? Because it's a monosaccharide. Of course it is. Of course it has a free anomeric carbon. D-ribose, all right, yes. Why? Because monosaccharides. All right, what about lactose? We just looked at that. Yes, that is reducing. There's a free anomeric carbon. Maltose. Okay, so we have our two glucose units, right? Our anomeric carbon. We have a bond with oxygen, right? Oop. This is our anomeric carbon that's free. So is maltose a reducing sugar? Yes, it is. Cellulose. Cellulose. Is that a reducing sugar? It is not, because the chains are so, you know they're chains, right? So only the ends are actually reducing. So that's considered as no. All right. And the same thing is true for starch, actually. Okay, that's it. That is it. Thanks for watching.